if we've got a rotating beam, and maybe I can find my domino down here. Okay, we've got a rotating beam with a mass m at distance r from the axis, angular velocity omega. We want to calculate the centripetal acceleration. And we have this relationship, which was derived in chapter 3, chapter before the one we're in. People didn't seem to be too aware of it, probably because mastering physics didn't really do that much with it. But you're going to have to be aware of it. And centripetal force is v squared over r. Centripetal force is a force back toward the center. That was derived with a little diagram that looks like this, and you should go back to chapter 3 and look at it. Because it's important to understand that. Okay, now, if I rotate this beam, you know that this thing wants to spin out. And if I rotate it fast enough, it does spin out. Okay. That shows that the friction holding that domino on the beam became insufficient to provide the centripetal acceleration toward the center. For the centripetal force to provide the centripetal acceleration toward the center. You have an increasing centripetal acceleration. As I sped the thing up, omega kept increasing until it got to the point where the centripetal acceleration, where the frictional force could no longer supply the centripetal force needed to accelerate the thing toward the center. Okay, that shows that there's an acceleration toward the center of, toward the axis of rotation, toward the center of the circle on which the mass is rotating, along which the mass is traveling. Okay, you can't travel along a circle without having a force that pushes you toward the center of the circle, because you have to keep being pushed to change your direction. Go back to Newton's first law, motion on a straight line, unless there's a force at constant velocity, unless there's a force acting on it. Okay, that force in this case, the force that takes this thing off of its natural straight line and into the circle, is your centripetal force. It's a result of the centripetal acceleration. If you multiply the mass times the centripetal acceleration, you get the centripetal force directed toward the center of its circular path. Now, v is the speed along the arc of the circle. Okay, in this equation, v is the speed along the arc of the circle. We ask you to express this in terms of just the Rm and omega. Well, that's easy enough to do. V equals R omega. Now, that's something you can memorize, but you'll never keep it straight unless you've got a photographic memory. You have to be able to make sense of it. And omega is your number of radians per second, R is your radius. A radian of angular position corresponds to a radius of motion along the arc, as we've said a number of times. So you get so many radians per unit of time. You multiply that by the radius, you get how far you move along an arc of that radius per unit of time, which is your speed. That's common sense. If you understand what a radian is, and I keep repeating this, then you won't write this down wrong. You won't write V equals omega over R. And of course, it'd be kind of natural, even omega squared over R, knowing this formula. Okay. This thing seems to have slid off. Let's straighten up the board a little bit. I have to. probably up crooked now. That's okay. Okay, V is R omega, anyhow. So now you got A equals V squared over R. Centripetal acceleration V squared over R. That's quantity R omega squared over R, which is R squared omega squared over R, just R omega squared. So your centripetal acceleration is mass times R omega squared. Now, we ran out of time. We had a couple of lapses with Zoom and didn't have time to finish talking about the third problem on the quiz. So that's going to be part of your homework to complete the third problem on the quiz. Okay, so there it is.